Today, we're building an array from a permutation. The twist: can you do it without using any extra memory, transforming the input array directly? It's a classic in-place challenge. Given a zero-based permutation array, we need to construct a new array where each element at index I is the value found at nums sub I. Essentially, we're performing a double lookup, first finding an index, then using that index to find the final value. The constraint is that the input array contains a valid permutation of numbers from 0 to its length -1. The straightforward approach is to simply create a new array of the same size. Then, we iterate from 0 to the length of the input array. For each index I, we calculate nums sub I and assign it directly to the corresponding position in our new result array. This works perfectly fine and is easy to understand. However, it requires allocating an entirely new array, leading to big O of n space complexity. While time complexity is optimal at big O of n because we visit each element once, the extra space can be a bottleneck in memory-constrained environments. The key insight for an big O of 1 constant time space solution is to store two pieces of information within a single array element without losing either. Since all numbers are less than the array's length n, we can use modular arithmetic. We'll encode the new value into the existing element. For each element at index I, its original value is nums sub I, and its new value should be nums sub I. We can store both by modifying nums sub I to be original value plus n times new value modulo n. During the first pass, we transform each element this way. In the second pass, we simply divide each element by n to extract only the encoded new value, effectively discarding the original value which is no longer needed. Let's trace this with an example. Nums is 0, 2, 1, 5, 3, 4. Length n is 6. For I equals 0, nums sub 0 is 0. Nums sub 0 is nums sub 0, which is 0. So we update nums sub 0 to 0 plus 6 times 0 modulo 6, which is 0. For I equals 1, nums sub 1 is 2. Nums sub 1 is nums sub 2, which is 1. We update nums sub 1 to 2 plus 6 times 1 modulo 6, which becomes 8. We continue this for all elements. After the first loop, the array will contain encoded values. Then in the second loop, for each element, we simply divide by n. For example, our nums sub 1 became 8. 8 divided by 6 is 1. This extracts the new value 1, and so on for the rest of the elements. After both passes, the array will be 0, 1, 2, 4, 5, 3. This is the correct permutation, achieved by storing and then extracting the new values in place. You'll spot this pattern when you need to perform an in-place transformation on an array where elements are within a known range, typically 0 to n-1. It's particularly useful when you need to store two pieces of information at one index without extra space, and one of those pieces can be recovered or is no longer needed after a certain point. This optimal solution achieves an big O of n time complexity due to two passes over the array. Crucially, it uses big O of 1 constant time space complexity by modifying the array in place. This in-place trick is powerful for space optimization. Try the next problem that involves array transformations. Same pattern might apply. Don't forget to like and subscribe for more DSA insights.